in continuation with the digital education initiative of Dr. APJ Abdul Kalam University. Here is another lecture of the series on the subject VLSI technology having subject code KEC 053. I am your faculty Sangeeta Mangesh from Department of Electronics and Communication Engineering, JSS Academy of Technical Education, Noida. In the last lecture, we have seen different species or dopant species, solid, liquid and gaseous, and how the like diffusion furnace also we have studied. In today's lecture, we are going to study the diffusion in silicon, that is the behavior of typical materials which are being used as a dopant in case of silicon while fabricating the microcircuits. And we are going to study the problems which are encountered while carrying out such diffusions. At the end of this lecture, I expect you to have understanding about the behavior of these common materials when you are carrying out the diffusion, and I expect you to take out like understand the behavior so that you get the perfect diffusion profile. Next, I expect you to analyze these issues like related to diffusion and perform remedial actions so that you can go for precise dopant profiles or attaining dopant profiles precisely. So, going ahead with typical impurity behavior in silicon, the typical impurity behavior I told you, like there are group 3 and group 5 materials which are being used, that is p type impurities and n type impurities which are being used, and the typical behavior is because of the substitutional and interstitial what you call interstitials within the silicon crystal, and movement is affected greatly by the concentration and the charge state of the lattice. That is whether the particular interstitialcy or vacancy is neutral, positively charged or negatively charged, and depending upon that you will have typical behavior of the dopant species within the bulk material. For example, boron, arsenic, aluminum, gallium and indium. Except indium, all impurities can be used or can show shallow diffusion profiles and can be used for junction formation. Group 1 and 8 materials which are typically used for some specific applications such as lithium, potassium, sodium as well as gaseous species such as argon, helium, they occupy interstitial sites in the silicon, are normally and they are electrically inactive. So, you do not have much impact because of these particular, or they do not have much impact on the overall device what that is being fabricated. Most many transition materials or transition elements such as cobalt, copper, gold, platinum and silver, they diffuse because of the interstitial and substitutional, and their typical behavior is because of the knocking. They have many of them have got have tendency to dislodge the host atom and occupy it, and therefore, that behavior totally alters from the normal material or normal diffusion profiles what we have seen, that is Gaussian and complementary error function profiles. They occupy both these sides, that is interstitial as well as substitutional, and there is also like difference solubility between these sites is being quite substantial. Dissociation of substitutional into an interstitial or vacancy is the mechanism which is involved in this in most of these what you call them transition materials, and therefore, you have typically deep lying impurities or they can penetrate deeper into the bulk substrate or silicon, and they have got specific applications related to their behavior. On the other hand, the knockout mechanism that is defined that is defining the diffusion in case of gold and platinum also shows like because of this particular knockout behavior, they also tend to get deeper into the silicon, and therefore, you have typical material or typical behavior which is being shown by the silicon. Okay. So, here let us see what we have. Okay. Now, when we see boron, like first arsenic we are seeing. So, arsenic is generally not being used. Arsenic is not being used because you have very few materials, okay, very few impurities which are being in color. I have selected, just a minute. whenever I am going for very low diffusion, like since arsenic has got very less diffusion factor, there is a problem with arsenic diffusion or with arsenic is whenever we are carrying out diffusion, it has got tendency to have out diffusion rather than actual diffusion happening within the bulk, and therefore, you have to prevent its like oxidation happening onto the wafer. Whenever you are exposing it to, like, oxidation once happens, rather than penetrating deeper, it will not get, like, you have something known as out diffusion happening, and therefore, the primarily the diffusion is happening because of the substitutional, and to some extent it is happening because of the interstitials. And therefore, whenever we are going ahead with it, you will see that the diffusion profile is almost similar to the, almost similar to the, it's like this is much different, like this is the common, this is the common mathematically modeled profile, this is the mathematically modeled profile, whereas in case of arsenic you will find totally different kind of profile which is being observed over here. It is much different. This is the arsenic profile of diffusion when carried out within bulk silicon, and the total behavior is because of the, primarily because of the substitutional sites, and it is very good to form shallow junctions. You can form very good shallow junctions with the help of arsenic. Then comes the most popular material, which is known as boron. Now, this boron when being used, this boron is very useful because this boron is that I am using, the boron is basically group 3 and has got very high misfit factor. Now, since it has got quite large misfit factor, the material can move within, or it can have, like you can, in presence of oxide, it can form constant diffusion, you can have very good constant, like almost error function like diffusion profile you can get. In presence of oxidizing species, the diffusion is observed applicable for fabrication of the isolation wells as well as for low threshold MOS circuits, typically in 100 concentration. Now, when you go for such profile, you will observe that the profile which is being shown over here, the profiles which are being shown over here, you will see that as the concentration is increasing, the profile is deviating from the error function profile. Now, as we go ahead, please understand, as this ratio is much closer to the concentration, you will have Ni, that is intrinsic concentration, it is reaching, then it is like see P by Ni, that is the ratio is becoming much less than 1, the profile is approaching towards the model profile, which is shown by the mathematical function, that is complementary error function. As you go away, the higher the value, you will have the diffusion profile getting deviated from the original mathematically modeled diffusion profile. This is what is again shown over here. This is being studied practically. The boron profile is varying so much, just see the deviation from the standard profile. So, this is the mathematically modeled profile and this is the boron profile which is being shown practically, and this is basically after the, like when being carried out, the measurements are carried out because of the sheet resistivity as well as the SIM, that is spectrographic emission dosing. You have measured the profile and this is what profile you have got, which is so much varying from the standard profile which is being shown. Then you have a typical material which is known as phosphorus. Now, phosphorus is the most common material which is used for creating n doped regions because it has got and therefore, when we are carrying out this particular impurity dopant profile, it has got very less misfit factor, and since the diffusion is limited by the solid solubility, now here you can have good concentration of almost 10 raised to power 21 possible in case of my phosphorus diffusion. The diffusion on phosphorus is associated first because of the doubly charged vacancy sites. Now, since you know already, the vacancies can be positively or vacancies can get activated or get charged when it accepts, because the vacancy is filled up by the hole, it will get positively charged, or vacancy gets filled by the electron, it can get negatively charged. So, there are different categories of vacancies which are available, and because of the charged species which are occupying those vacant sites, the behavior of the diffusion will change, or the profile what we get after diffusion will alter, and that is what is happening in case of phosphorus. My diffusion species are getting, okay, they are basically acceptor vacancies, and these vacancies are doubly charged, that is you are having 2 minus charge available on the vacant sites. Now, because of this doubly charged vacancies, there is penetration or diffusion profile which is being shown like this. Just see, this is what is the diffusion profile what we see. But after the diffusion happens for certain concentration or certain what you call charge level, after beyond that what happens is these diffusing species will alter. Now, you have something known as bulk intrinsic concentration, and when you are adding diffusion or you are adding impurity into it, the Fermi level will alter, Fermi level will shift from conduction band towards the mid band, and this shift in the Fermi level, this shift in the Fermi level by almost 0.11 volt, 0.11 electron volt will change the behavior of species or energized species within this bulk. Now, what happens at this point of time where the species start dissociating. Now, when the dissociation happens, rather than doubly charged species, they get converted into singly charged species, and when they get converted into single charged species, large number of these V minus gets generated, and thereby these can get further deeper, like penetrate further deeper into the substrate, creating a tail region. Now, what is this tail region? This is what is the tail region, the point where normal profile is converted because of the dissociation into deeper like variation from the normal profile. We call it as a kink, and this kink behavior is being seen in phosphorus diffusion profile. But beyond the kink, you will have a tail region where you will have concentration getting reduced or concentration changing up to 10 raised to the power minus 12 centimeter per square, and which is much less than the intrinsic diffusivity. Okay, it is much less than the intrinsic diffusivity at 1000 degrees centigrade, and therefore, phosphorus is almost okay or is a common material which is used for formation of tubs or N type tubs within the silicon substrate. So, whenever we are fabricating devices or especially CMOS devices, you create first a tub to isolate your device, and phosphorus is the common material which is being used, which are because of its behavior within the tail region. We have seen already, this is the behavior. Initially, you are having doubly charged, that is PV2 minus, that is doubly charged what you call vacant sites, which are responsible for creating diffusion profile in this manner. But after that what happens is the Fermi level shifts, that is energy level shifts, these start getting disassociated, and once they get disassociated, instead of singly charged doubly charged, they become singly charged vacancies, and the diffusion profile then gets enhanced, and you will have further deeper penetration into the tail region. Now, this typical behavior is also known as kink. This is what is being shown. As you keep on reducing concentration, please understand, as you keep on reducing concentration, the profile will be much closer to the error function profile which is being mathematically modeled, but as you keep on increasing the profile, you will have this kind of kink behavior in the tail region. Now, this impact of this typical behavior of the diffusion profile when you carry out for N type impurity getting introduced into the silicon gives a typical what you call behavior in my N type of transistors, which is known as emitter push. Now, what happens in my N type transistors? I am having N region as the base region, then I am having this is my emitter region, this is my base region, and this is my collector region. Now, whenever I am having heavily doped p type phosphorus impurity, I am penetrating into it. Now, this area will be responsible for the tail phenomena which is being observed. Now, since the tail phenomena will increase, the like dissociation will happen and there will be increased diffusivity. Now, because of this increased diffusivity, there will be enhanced diffusion in case of boron also. This is what is being shown over here, or this is what is being written. Now, when you have NPN bipolar transistors employing phosphorus diffused emitter region, the boron diffused base region in or like which is inside the emitter region is is basically it is approximately 0.6 micrometer than the outside emitter region. It is inside this particular thing, and the dissociation can result into further deeper penetration of this species or boron species, and that is giving birth to the emitter push effect. So, below emitter the boron diffusion profile also alters and that is called as emitter push effect. Since below the emitter the boron profile is changing, we call it as emitter effect or emitter push effect. The diffusivity of boron under the emitter region is also enhanced because of the dissociation. Now, this is also, now please understand, I also told you, though the misfit, like since the misfit factor is very large in case of boron, when I am designing my NPNs, please understand, when I am designing my NPN transistors, I can have very large concentration of emitter. You know, emitter region is very heavily doped. So, when I am going for material that is phosphorus for carrying out good like heavily doped profile, I am easily that can be easily attained using phosphorus. Whereas, if I design PNP transistors, please understand, if I design PNP transistor, I need to go for diffusion profile or emitter region which is being designed or which is being created by boron diffusion. And since the boron has got very large misfit factor, it is very difficult to attain high concentration profiles. And this is also one of the reason from VLSI fabrication point of view that PNP transistors are not preferred. Always people or anybody will go for the device which is easily which can get easily fabricated, and therefore, normally rather than NPN, PNP transistors are difficult to fabricate and therefore, they are not being preferred. So, this is emitter push effect which is strongly observed, and you need to take care of this effect whenever you are fabricating the devices. So, phosphorus has got typical behavior which is deviating from the standard modeled error function profile. We have seen the mathematical model to understand the phenomena of diffusion, but practically there is drastic what you call alteration or modification or behavior change, and that behavior change we have seen in boron, we have seen in arsenic, we have seen in phosphorus. And phosphorus, there is typical behavior change because of the movement of species within the bulk through doubly charged vacant sites. Then comes, this is what is exactly being shown over here. This is the what you call it, this is the region, and this is what is the emitter region pushing the base region, and therefore, we call it. So, this is what exactly being shown. This is the kink effect being observed over here, phosphorus. This is the emitter. Now, beyond this kink, whenever there is disassociation happening, there is sudden increase in the diffusion profile, and since this sudden increase in the diffusion profile will also go for boron, that will get like boron diffusion profile also will get affected, and further it will create this is what is this is the modification in the base region, and therefore, since the emitter is pushing, this is because of the pushing of the emitter, we call it as emitter push effect. So, this is calculated measured boron phosphorus in case of my NPN transistor, and this is basically showing you the emitter push effect at 1000 degree centigrade for 1 hour, followed by 900 degree centigrade 45-minute steam oxidation. Now, you have something known as deep lying impurities. Whenever you carry out, so far we have seen normal diffusion profiles for typical materials like boron, arsenic and phosphorus. Then comes the typical materials which are like being diffused for particular applications, and those materials we use for normally are used for, we call them as deep lying impurities. Now, why those deep lying impurities are being used? Those are used for particular application, basically to control the or to check the minority carrier lifetime or control the leakage current. Like basically we need to control the leakage currents, and therefore we go for such kind of deep lying impurities. Now, what is this impurity, or why these things are being done? Now, diffusion by interstitial or substitutional mechanism at 5 to 6 order magnitude is faster than the substitutionally diffusing materials, and as a consequence large number of crystal defects arise when you have deep like you have these what you call materials diffusing into the silicon. Diffusivity is also a function of temperature and concentration. Please understand, whenever there is diffusion happening because of the interstitial and substitutional mechanism at 5 to 6 order magnitude faster than the substitutionally diffusion material, like whatever normal material getting diffused, if it is enhanced, like there is enhanced diffusion, there is tendency to form the crystal defects. So, whenever we are carrying out diffusion in presence of some oxidizing ambience or some other what you call enhanced diffusion, when you carry out, you have to ensure that there are minimum crystal defects. Similarly, like another thing is diffusivity is also function of temperature, concentration, and you cannot model such behavior with the mathematical models which are available. Upon freezing these impurities, that is, once you make these impurities stable or reside into the, they can be electrically active or they can be electrically inactive, and the sites at which these diffusion material or diffusion atoms are residing, you can only study their behavior once you carry out the characterization. In the next lecture, we are going to see also how the characterization techniques are being used. Now, once you do characterization, then only you can study the actual behavior or how actual material, how it has like penetrated into and how the profile has been created. The diffusion of these material is predominantly impacted by the, like whenever you are having any diffusion, you have to take care of the surface defects, because surface defects critically impact the diffusion happening within the bulk. If you have these deep lying impurities, these deep lying impurities can reduce the lifetime of the minority charge carriers and increase the current or increase the, like there is increase in the leakage current when you are going for p-n junctions. The impact further worsens when you elevate the temperature. Now, how do you carry out these particular impurities? Like many times you use them for carrying out or specific, like when you want high speed devices, you want to reduce the minority charge carrier lifetime, you make use of such deep lying impurities and you try to control the charge carrier lifetime. So, first typical material which is being used is the gold. Now, for high speed saturated logic circuits, to reduce the lifetime, I told you just now, we carry out these deep lying impurity profiles, and that is being done using gold. It is a common thing. Gold atoms move into the silicon at the interstitials, and subsequently they knock the host atom and occupy their locations and substitute those host atoms, and be, like further they keep on, like since they are active, again when at any modification or any elevated temperature, they further penetrate into the material, again dislodge the another atom, and this is how they have tendency to get deeper into the bulk material. The diffusivity is strong function of the concentration at which the interstitials are appearing or presence of interstitial is existing within the bulk material. In n-type material, the solubility is enhanced due to this gold which is available into Au minus state, that is minus like it is in the Au state, like it has got excess electron, that is it is since it material, and since the silver, okay. So, you have gold having minus electrically negative charge, and since the species which are penetrating are electrically negative, they have tendency to go deeper into the material when you are using n-type material, whereas it depends upon the background concentration and relative Fermi energy level at which the like where the Fermi level energy level is. whereas in case of p type material they behave as a donor impurities. Okay, they behave. So, gold diffusion is therefore to be carried out as the last step when you are carrying out the fabrication. Already when you have introduced different dopant profiles at different concentration levels, last thing is the gold dopant profile being created in within the silicon bulk when the devices are being created, and you want the deep lying impurities or deep penetrating impurities are to be introduced, such as gold. Second impurity which is being used is the platinum. The impurities are highly symmetric, like impurity levels in silicon or for platinum are highly symmetric, asymmetric basically, their behavior is asymmetric, then they cannot be they can be used for a lifetime carrier, what you call control on the lifetime carrier, and their proportional increase in the increase in the leakage current. They are very suitable for high voltage devices where the leakage current is the issue, and that is to be critically optimized when you need to optimize the power, because you have better controllability on the lifetime. You have got you can reduce the minority, and you have like without creating leakage current you can reduce the minority charge carrier lifetime, and therefore it is typically used for low power applications where addressing the leakage current or reducing the standby power or leakage, like you need to improve the standby power, like you need low power consumption when the device is in standby condition, and therefore for such applications this is very suitable material which is being used for creating deep lying impurities. Another major issue what you need to study in this case is the redistribution of dopant. Now, whenever you are creating the device, you know already the device is being created by you use normally a mask which is made up of SiO2. Now, when you are using SiO2 mask, you are creating the opening within the mask and introducing dopant within this. Now, when you introduce dopant, the penetration or the depth, if it is 1 micrometer and you have gap of also 1 micrometer, this is the gap of also 1 micrometer, there is every tendency that the diffusion happens laterally, vertically as well as horizontally. When the lateral diffusion happens, the rather than having only 1 micrometer, you will have some 0.5 micrometer happening here also, 0.5 micrometer happening here also. So, that means instead of 1 micrometer vertical and 1 micrometer horizontal, you will have 2 micrometer horizontal and 1 micrometer vertical. So, to prevent this to happen, whenever you are using oxidizing like you are using silicon dioxide as a mask, you need to study the behavior of the material or these dopant species when you are at the silicon dioxide interface, and that is being studied, under this particular redistribution of dopant category. Here we are taking care of something, always we have studied that whenever you are fabricating the device, you have something known as initially pre-deposition, and then we carry out the driving phase. That is, initially you have complementary error function profile, and then you get into the Gaussian profile, but and you have grown simultaneously in two-step diffusion. But in case of thermal oxidation, like when you carry out these kinds of what you call device fabrications are being carried out, the distribution will alter, or at SiO2 interface the movement will be totally different, and this movement will be governed by something known as M, that is the segregation coefficient. Now, this segregation coefficient is basically ratio of thermal equilibrium dopant concentration in silicon to thermal equilibrium dopant concentration in SiO2. Now, if the value of M, that is segregation coefficient, is less than 1, then the growing oxide depletes the silicon from impurities as the dopants segregate into the oxide. Even if M is equal to 1, the dopant depletion is observed because there is large volume for redistribution offered within the growing oxide by the growing oxide. Similarly, when M is greater than 1, you will have oxide ejecting the excess impurities back into the silicon. Now, this is what is the profile you will see. You have concentration, that is M less than 1, here you will have M less than 1 when you are having faster diffusion. Just see, here this is slower diffusion, this is faster diffusion. So, at the silicon dioxide interface, though the value of m is less than 1, there is sudden change in the diffusion profile being observed. Similarly, here also the impurity concentration at the oxide silicon interface is for different values of m. Here you are having m greater than 1, slow diffusing species, and here you are having higher like faster diffusing species, and the value of m is higher than 1. So, diffusion profile is totally changing within the oxide and within the silicon dioxide. So, this redistribution of dopant is happening at the silicon dioxide interface. So, you have to, whenever you are fabricating the device, you need to take care of these factors also, so that you get precise diffusion profiles. Once your idea about the redistribution of dopant is clear, what exactly is the deviation from the original diffusion profile is clear, you can easily answer like get the precise diffusion profiles whenever you are actually or practically fabricating the devices. So, let us put a stop over here. If you are able to answer the diffusion of boron, phosphorus and gold in silicon, you can list the applications of these dopants when you are going for microcircuit fabrication. You are able to check out the VLSI technology perspective. Why do you need and why do you prefer for NPN transistors rather than PNP? Because dopant profile emitter heavy dopant profile is easily being attained. Then if you are able to go for how impurity redistribution happens, what is exactly load like it behaves, how that segregation coefficient is impacting the redistribution happening at the oxide silicon dioxide interface. If you are able to analyze that, you will be able to consider or understand how difficult it is to get the precise diffusion like dopant profile within the silicon and design a device of having desired electrical characteristics. So, once it is clear, let us go ahead with the next lecture, which will deal with the evaluation of the diffusion profiles.